Hello everyone. In this presentation I am going to discuss how USGS, U.S. Fish and Wildlife Service, and the National Park Service has integrated machine learning technology into northern sea otter monitoring protocols. Through the development of these methods, we have simplified and automated the end-to-end photo processing pipeline for aerial wildlife surveys through the creation of a computer application named SeeOtter that guides users through the entire data generation process from raw imagery to clean georeferenced datasets. My name is Colin Power. I am a contractor and ecologist that has been working as part of this team for the past 3 years, and I'm a co-developer of the SeeOtter application. In this effort, our three main questions were: how do we make SeeOtter surveys safer, more reliable, and more efficient? SeeOtter habitat in Alaska can often be very remote, with vast, rugged coastlines and extreme conditions, making long-distance aerial surveys the status quo for population monitoring. Counting sea otters in aerial imagery is an essential task, but it's time-consuming and prone to human error. Manual methods can take hundreds of hours, and results often vary between observers. While AI offers a solution, deploying these technologies usually requires specialized expertise in machine learning. Our team developed the SeeOtter application to bridge this gap. SeeOtter makes AI-assisted pipelines accessible, providing an efficient way to process wildlife imagery without needing extensive technical knowledge. This interface is designed to streamline image validation. Here you see predictions where detected sea otters are outlined in green boxes, and users can validate each detection with simple buttons for correct, incorrect, or ambiguous classifications. The application also displays metadata like latitude, longitude, and altitude, ensuring that users have all the information needed to accurately access each image. This interface enables fast, efficient validation while keeping essential data at the forefront. SeeOtter automates the entire photo processing workflow. It starts by organizing and backing up data. The application then corrects for image artifacts like vignetting and overlaps, and applies the AI model to detect otters, then guides users through validation. Finally, it georeferences the images and individual otter locations, outputting clean count data in CSV and shapefile formats. This streamlined workflow turns raw imagery into actionable datasets, ready for ecological analysis. Here I will give a quick demo of how SeeOtter functions from start to finish. So here we're able to go in there and back up our photos. This is essential in maintaining data integrity and being able to look back at what our raw data was later on in the future after we do a couple altercations. So here we generally recommend doing about 3 backup files. We usually like to put these on different drives so you can have them safely in different places. If one drive fails, you still have backups in several different places. After you back up your files, you're able to go in there and we're able to set up our file paths so we have a clear, replicable way to have this data represented within our file system. So generally we have a location we set, as well as what camera the survey was taken on, and then we have date location information like the year and then the month and the date. This allows us to organize the files efficiently and be able to look back at each survey day as an individual unit. We are actually able to select from multiple source folders, so if you have multiple cameras, you're able to set them up to all kind of go in this file format. It takes a lot of the guesswork out of, where do I put all my files, and what is the best way to organize these. After we organize these photos, we're able to go in there and extract the metadata. And what we're doing when we extract the metadata is pulling out each individual lat long from every single photo, as well as altitude data, date, time, camera settings, whatever additional data we have that helps us visualize these photos in the future. So not looking at actual otter locations yet, we're just looking at where these photos were taken, when they were taken, things like that. That helps us organize our photos along transects and select what is on transect and what is off transect, as well as identify which photos we actually want to process and the data that we're interested in. This metadata extraction is one of the most important steps because it allows us to accurately georeference all of our data and create accurate maps in the future. After we extract this metadata, we can start assigning transects. I'm not going to go into the details here, but you're able to identify your start and end locations of where each transect is located. After that, we're able to pre-process photos, so we're able to set a crop to get rid of vignetting or any overlap that we have, as well as correct any GPS errors. You can change your model weights, as well as go in there and change different things like image tags or your annotation categories that you're interested in. Here we're looking at otters and pups, but you can also put in things like test or whatever you're interested in. And then you can start the SeeOtter application, which is going to get you to processing these actual photos. So now everything is organized and set up, and we're going to go, use this AI assisted method to process our photos and then validate all that data. Here we can classify images as land or water. You're able to go in and select the folder which your images sit in, as well as where you want to save your results files. This just uses a simple land classification machine learning model that we developed. We're not going to trust all the predictions from the models right away. We want to get eyes on every image. So here we're going to validate our water images. So what the model predicted as water. We can see that one has a little bit of land in it, but the rest all have water. So we're able to go in there and separate these out and correct the model. Here we're able to identify the percentage land cover in each image based on the separated images that the model created. You can go in there and simply click on these grid cells and get a pretty accurate to the 1% level of how much land is within your image. From there, you're able to accurately classify total effort, and you're not including any land in your survey effort when you're looking at aquatic species. After that, we're able to generate a simple CSV that gives us percent cover. Here's that results file that we generate from that land water classification. So you can see that we have clear image file names as well as whether they are land or water photos. And then you have a percent land cover in those photos that are identified as land. So this allows us to go back in, correct effort to make sure we're not incorporating any land into our final survey effort. You can also use this similar method to look at other habitat attributes like kelp cover, ice cover, etc. So after classifying images as land versus water and developing a percent cover estimate, we can go in there and actually do our object detection on our SeeOtters. So we're going to go in there and start a new survey. You can give it a project name and then identify where your project path is located. Go back to where we're setting things up earlier. So when we set those things up in the earlier steps, it makes it super easy to just point and click here, hit that folder, and then we have a fully formed survey. So it's going to take a little while for the survey to load up, and I just did 9 images as an example, as opposed to the thousands that we get every day. But here you can just press play, and that'll load up our object detection model and start predicting on our survey. So this can take a little bit of time depending on what system you're running. Right now on my laptop it's a little slower, but generally on a high processing computer with a GPU, you can get about 1 image a second if you're processing full-size photos. So this time is variable depending on how big your photos are and what size your model is. After your model is finished running its predictions, you can use the SeeOtter window to kind of view survey information. So you can see how many images you have, what's been processed, how many total predictions you have, and so forth. It just makes it really clear for data integrity and clarity. So here we go into the validation window, which is the most important part of this. We use the AI model to identify potential otters, but then we still get a human to go in there and validate every single individual prediction. So this allows us to have near, perfect accuracy because we're not trusting the model 100%. The model does well in picking up things that could look like otters, but then we go in there and give them either the correct, the incorrect, or ambiguous. So sometimes you can see things that aren't quite an otter, but you're not sure. So you can mark it as ambiguous to go back with a team later and review that actual mark. Here you can see it's pretty simple to go through a bunch of images and filter through these predictions pretty quickly, as opposed to having to scan through every single little bit of an image. You can mark things as incorrect or correct, as well as change things like your confidence threshold. So here you can see we're picking up a lot of kelp, so we can adjust the confidence threshold so our model's a little more picky on what it calls an otter and what it doesn't. We generally set our confidence threshold about 0.4. That's a good cutoff on picking up most of the otters while eliminating a lot of that kind of those trash predictions. You can also go in there and add predictions as well. Here we see a potential pup next to this mother otter. So you can go in there and identify, what you want to put in there, and you can create your own annotations as well. So if the model misses anything, you're able to go in there and add those annotations personally. This validation step, in conjunction with the model's speed and efficiency, allow us to have great confidence in our predictions and final data sets that we create. Here we can generate that final CSV, which georeferences all the data and then creates a point count of every otter location as well as every image that we took. So we were able to generate an effort layer as well as a total final otter count with georeference locations. This dashboard provides an overview of the processing state, survey details, and prediction results. Users can initiate pre- and post-processing, manage files, adjust survey settings, and run your object detection model. This allows users to monitor and manage all aspects of the processing pipeline, offering control and transparency over each stage of data generation. Our experimental trials highlight SeeOtter's value. The AI-assisted approach aligns with the variation seen in manual counts between experts, delivering more standardized and repeatable results. Importantly, it reduces the time needed to process a day's imagery from 166 hours to approximately 4 hours, a 4,165% improvement in efficiency. This allows us to process larger data sets, ensuring timely and accurate monitoring. In addition to detecting sea otters, this process also captures images of other species, including cetaceans, seals, sea lions, bears, and seabirds. These opportunistic sightings reveal the potential for sea otter to expand beyond a single species focus, opening up possibilities for multi-species surveys. By leveraging this capability, we could streamline broader ecological monitoring efforts, providing valuable data on multiple species with the same survey flights. Since its deployment in 2022, SeeOtter has supported large-scale sea otter surveys across Alaska, analyzing thousands of kilometers of transects and handling dozens of terabytes of imagery. After initial funding by U.S. Fish and Wildlife Service, our work was also recently awarded a USGS Community for Data Integration grant, ensuring continued development. SeeOtter is designed to be generalizable, supporting various camera systems, target species, and AI models. By simplifying data processing, it increases accessibility for conservationists and ecosystem managers.